So the topic for today's video is coterminal angles and reference angles. Ignore me, I'm just making sure my pen works. Yep. The objective is if I give you an angle, you can find angles that are coterminal to that angle, and you can find the reference angle for that angle. Right now, these definitions aren't going to mean very much. I promise you they're very relevant to trig, because coterminal angles and reference angles, or two angles that are coterminal, have very similar trigonometric properties, and reference angles sort of the same idea. Right now, it's just going to be like definitions. It's sort of like when you learned about supplementary and complementary angles, and they didn't really mean anything to you at first, but then sort of as you did more geometry, you saw how they kind of came in with proofs and stuff like that. So right now, these are just going to be kind of like generic angle relationship definitions, but I promise you in time they will be very helpful, especially reference angles. This one's like everything, right? So this is a big one. Okay, so let's get right into it. So let's start with coterminal angles. So what are they before we talk about how to like calculate what a coterminal angle would look like? Coterminal angles look exactly the same in standard position. So if two angles are coterminal to each other, it means that when you draw them in standard position, they don't look any different. They look exactly the same. Now, if you don't remember, standard position means it's on a coordinate plane. It means that their initial side is the positive x-axis, and then the terminal side sort of rotates. So you can imagine if you're rotating the terminal side, what would you have to do to get it to end up in the exact same place? Okay. In other words, the terminal sides have to be the same. The initial sides are automatically going to be the same, right? So they're coterminal, means the terminal sides are on top of each other. So what would that look like? So what are two angles that would look exactly the same in standard position? And maybe you're already thinking of sort of how that would work. If you're not sure, or if you just like are waiting for me to tell you, I'll just tell you. A 30-degree angle is coterminal with a 390-degree angle. And if you don't believe me, let's draw both of them in standard position, and you'll see that they're actually right on top of each other. Okay, so if you sort of imagine a 30-degree angle, here's the initial side right here, the positive x-axis. And then a 30-degree angle, roughly speaking, this would be 90 degrees if I went all the way up to the y-axis, right? So a 30-degree angle would be like here-ish, okay? And then that would be 30 degrees, okay? Now, the thing is, if I wanted to draw a, a 390-degree angle, it's going to be in the same color because I don't really know how to change color. Well, let me try. Why not while we're here? Sorry, this takes a second. Ooh, let's do it in blue. Yeah, okay, let's do it in blue. So a 390-degree angle, same initial side, right? So that's always the same. And now I'm going to rotate the terminal side 390 degrees. Now notice 390 is bigger than 360, which means I'm going to go all the way around, right? That's 360 degrees. And then how much do I have left? An extra 30 degrees. So I'm going to go all the way around 360 degrees and then a little bit more to right here. And you can see that that 390-degree angle and that 30-degree angle look exactly the same in standard position. Because all I really did with a 30 was add 360 to it. So I just added a full rotation, and that means I rotated my terminal side all the way around an extra 360 degrees. That's really all there is to coterminal angles, right? It's really just adding 360 degrees will get you right on top of yourself again. In fact, there are infinitely many angles that are coterminal with a 30-degree angle. You just got to keep adding or subtracting 360, right? Because if you subtract, you rotate in the other direction. So like, for example, 750 is coterminal to a 30-degree angle. So if I draw my 30-degree angle back again, which I just drew on the last slide, there's a 30-degree angle, approximately. I'm sketching, right? If I think about a 750-degree angle, well, 720 is two full rotations, right? So I'm going to go all the way around the block, all the way around the block again. And then to get to 750, I have an extra 30 degrees, so I'll be right back there. So 750, same thing. It's just like I rotated around twice instead of just rotating around once, okay? Similarly, like let's do green. Negative 330 will be rotating down. So instead of rotating 30 degrees up, I'm going to rotate 330 degrees down. Well, 360 would be all the way around, so I'm going to stop 30 degrees short of that. It's going to end up right there, okay? So rotating 330 degrees down or 30 degrees up, same difference. Okay, so there's literally infinitely many. You could just subtract 360 again, that would get you negative 690, that's coterminal. You could add 360 again, that would give you what, 1110, that's coterminal, and so on, right? So you can really do this forever and ever. And that's all there is to coterminal angles. It's really just this idea that as you add or subtract 360, the way these angles look is just going to repeat. Okay, and we've seen something similar to that in a previous video, I think, but just to kind of give it a little more oomph. Calculus is always in radians, though, so I want to mention what coterminals are like in radians. It's the same basic idea. The only thing you have to remember is that 2 pi radians is 360 degrees. So instead of adding or subtracting some multiple of 360, you're going to add or subtract some multiple of 2 pi, right? So if I had like 5 pi over 6 and I add 2 pi to that, let's write up here 5 pi over 6 plus 2 pi would be 12 pi over 6. Just to make it simpler, I'll make the common denominator right away, right? 2 is 12 sixths. So yeah. So 5 pi over 6 plus 12 pi over 6 would give me, that'd be 17 pi over 6, right? That would be one. Or I could subtract 2 pi. So let's select different color. Now that I know how to change colors, this is a good tool. 5 pi over 6 minus 12 pi over 6, right? Same thing, it's just 12 pi over 6 is 2 pi. I'm just subtracting now. And if I subtract, I would get, well, what's 5 minus 12? Negative 7 pi over 6. Okay. Or I could add 2 pi over 6 again, get 29 pi over 6, and so on. I think I actually have those three written. So yeah, 17 pi over 6, 29 pi over 6, negative. How to get negative 11? Negative 11 pi over 6. 5 minus 12. No, this is wrong. This is correct. Good thing I did it. See? Look at that. I would have just written something totally incorrect right on there. Yeah, but 5 pi over 6 is the same thing as negative 7 pi over 6, I believe. So there you have it. Even I make a mistake sometimes. Ignore that. Oh my God, I'm so ashamed. Ignore that. Yeah, negative 7 pi over 6 is correct. Good thing I did it. Okay, reference angles. Let's talk a little bit about these. These are, again, very useful because an angle has incredibly similar trigonometric properties to its reference angle. But right now that means absolutely nothing to you guys because you're like, well, I don't know. I haven't gotten to unit circle trig yet, right? But when we get to unit circle trig, you'll see that actually reference angles are the key to the whole thing. Until we learn that, though, it's going to be a pretty arbitrary definition. If you have an angle in standard position, the reference angle is the acute positive angle between the terminal side and the x-axis. Okay, so reference angles by definition are always positive, so you can't have a negative reference angle. They're always acute angles. They cannot be obtuse angles, so they always have to be less than 90 degrees. And then between terminal side and x-axis. Now keep in mind, like if I have a coordinate plane, this whole thing is the x-axis, right? So not just the positive x-axis like we use for the initial side, the whole x-axis, okay? This is sort of the catch-all definition, but sometimes it's easier to think of reference angles as dependent on what quadrant you're in. So let's look at sort of like, here's 4 different angles, each one in a different quadrant. In the first quadrant, you'll see that the acute positive angle between the positive, or between the terminal side and the x-axis is just the same angle, right? This angle is positive and it's acute. So this is sort of the reference angle right here. In the first quadrant, the reference angle and the angle are the same thing. So it's not really interesting in the first quadrant. In the second quadrant, you can see that the acute positive angle between the terminal side and the x-axis is actually this angle right here, right? It can't be the original angle because that's not acute anymore, right? And so it's got to be the angle between the terminal side and the x-axis. We're going to this part over here. That's the reference angle. Okay, so if you had this angle, if this angle was theta, to find the reference angle, you would have to do, well, the whole thing's 180, and then you would subtract the theta to figure out what was left. So in the second quadrant, it would be 180 degrees minus theta, right? In the third quadrant, you'll see that actually, like, this is the reference angle, right? So here's my terminal side, the acute positive angle. You can't use the whole thing because it's not acute anymore, right? You can't use this angle because that angle's not acute either. So you have to use this angle right here between terminal side and x-axis. So that's the acute positive angle between the terminal side and the x-axis, right? And now it's sort of the same. It's like this much right here from here to here. That's 180 degrees. So I need to sort of what's left. So I have to do, instead of 180 minus theta, I have to do theta minus 180, right? So I have to take the full rotation and then subtract off this piece to get what's left over here. In the fourth quadrant, this is my angle, this is my reference angle, right? Between terminal side and x-axis, acute positive angle, right? Just to call your attention, make sure you don't go to the y-axis, right? That would be a terrible idea. It's always to the x-axis, to the x-axis, to the x-axis, okay? And in this case, hopefully you can see this one's not so bad to see. All the way around the block would be 360 degrees. So to get this reference angle, you would do 360 degrees minus theta. And of course, this one's just theta. So depending on what quadrant you're in, you're going to use something slightly different for the reference angle computation, right? But what you're actually looking for is the same thing every time. It's the acute angle between the terminal side and the x-axis, okay? So let's do some examples. Let's find the reference angle for these 5 angles here. And once you get good at this, it goes pretty fast, but you probably need to draw the angle in standard position first. So let's do that. A 135 degree angle is going to be, here's the initial side. Maybe I should use a different color. No, I think it's fine. Here's the initial side. 90 degrees would be here, so 135 is going to be in the second quadrant. It's going to be sort of that much, right? 135 degrees. Okay. Now, the reference angle is going to be the acute positive angle between the terminal side of the x-axis. It's going to be this angle right here, right? Terminal side x-axis. So the whole thing all the way from here to the other side would be 180 degrees. If I do 180 degrees minus 135 degrees, what does that give me? 45 degrees is the reference angle for this one. Okay, cool. Let's look at the next one. 248 degrees. So 248 degrees, well, 270 would be 3/4, right? So 270 degrees would be to here because it'd be 90, 180, 270. So it's not going to quite be that far. The initial side's still going to be the same as always. And the 248 degree angle is going to be sort of over here, right? And then this is going to be 248 degrees, okay? So if that's the angle, where's the reference angle? Well, the reference angle is going to be this little piece right here. And because we're in the third quadrant, I'm going to take the full angle measure and subtract off this 180 to give me just a little red piece that's left. So I'm going to do 248 degrees minus 180 degrees. And what's that going to be, 68? So that's the reference angle for a 248 degree angle. Moving right along. 313, I know 360 is all the way around, and I know 270 is to here. So we're going to be in the fourth quadrant. Again, I'm just sketching these. They're not very precise. I don't have a protractor to measure, but as long as I'm in the right quadrant, I can get a good look. So 300 and, what is this? Go away. I'm in the middle of something. I'm busy. Okay, 313 degrees, right? Now, that's the angle. Let's look at where the reference angle is going to be. The reference angle is going to be, again, between terminal side and x-axis, so this one right here, right? Never the y-axis. Again, I want to reiterate that point, always the x-axis. So 360 would be all the way around, but I don't want all the way around. I want to stop just a little bit short, so I need to figure out how much is left. So I'm going to do 360 minus 313. And what's 360 minus 313? Is it 47? I always get a little stuck. Hold on, I'm going to double check. I don't want to write something incorrect like I did already once before. Okay, 47 degrees. Cool. Moving right along, I have a 370 degree angle. Now that angle is a little too big because 360 is all the way around, so it may help me to write a coterminal angle. So a 370 degree angle, if I subtract 360, is the same as a 10 degree angle, right? So I can draw a 10 degree angle very quickly. A 10 degree angle is just sort of a tiny little angle that's just in the first quadrant, just barely an angle at all, just like that, okay? Now 370 would be all the way around, then plus an extra 10, but it looks the same. As far as the reference angle goes, reference angles in the first quadrant are always the easiest because they're just the exact same thing. So the reference angle in this case would just be 10 degrees. Okay, it would not be 370 degrees though, because that would be not acute, right? That would be a very obtuse angle, incredibly obtuse. Negative 108 degrees. So here's the initial side. If I did negative 90, I'd be here. So I'm going to be a little more than that, which means I'm going to be in that second quadrant. Nope, that third quadrant. This is the second quadrant. So I'm going to be in that third quadrant. Where's my reference angle going to be? It's going to be this angle right here, right? And this one's kind of interesting because I don't really know what this angle is, sort of the big one. I could easily figure that out, right? I could do plus 360 to figure out a coterminal angle. But I know that this part right here, from here to here, maybe I should use a different color. Let's use like a blue or something. Okay, this part right here, I know is 108 degrees. And I know the whole thing is 180 degrees. So if I took 180 and I subtracted 108, what would I be left with? 72, right? 180 minus 108 would be 72 degrees. So the reference angle in this case would be 72 degrees. Okay, so yeah, there are like sort of, you can memorize in quadrant 2, you subtract from 180, in quadrant 3, you subtract 180 from the angle, but it sort of is more helpful to just draw the angle itself and then sort of analyze it for a second and use your geometry and your spatial skills and stuff like that and sort of piece together what you have to do from a math perspective, because it's different every time depending on where the angle lies, okay? I want to talk a little bit about reference angles for radians, but actually reference angles for radians are easy for most of the angles that you're going to have to deal with, right? So you don't often see in trig angles that end in like an 8 or a 3 or stuff like that. They're usually like, you know, the angles we're used to, the 30s, the 60s, the 45s and stuff like that. Actually, this is where one of the very few places where people prefer to do a radian calculation over a degrees calculation. I can do all these reference angles in like 3 seconds in my head. I don't even have to draw a picture. I already know. The reference angle for 3 pi over 4 is pi over 4. The reference angle for 5 pi over 3 is pi over 3. The reference angle for 11 pi over 6 is pi over 6. For 2 pi over 8, that's the same thing as pi over 4, so it's pi over 4. And for negative 2 pi over 3, it's pi over 3. And I don't even have to draw or think or do anything because I've done this so much that I know that that's sort of the case. If you have your angle in simplest form, for most of the ones that we're actually going to deal with, the pi over 4s, the pi over 3s, the pi over 6s, the pi over 2s, your reference angle comes for free. You just sort of look at the denominator and then you're in business. If you don't believe me, we can run through it real quick. 3 pi over 4, well, this is where it gets a little tricky. Remember, pi is 180 degrees, so 3 pi over 4, this would be 1, 2, 3, 4 pi over 4. So if you didn't follow me with my cursor, this would be 1 pi over 4, this would be 2 pi over 4, this would be 3 pi over 4, and this would be 4 pi over 4, right? So 3 pi over 4 is right there. And then the reference angle would be this angle, and what am I left with here is pi over 4, okay? 5 pi over 3, we can go through the same process. Here's the initial side. Okay, 1 pi over 3 means that we have to go sort of 3 steps to get to pi, because pi is 180. So this would be 1 pi over 3. That would be 2 pi over 3. That would be 3 pi over 3, right? And then this would be 4 pi over 3. This would be 5 pi over 3. And then this would be 6 pi over 3. So 5 pi over 3 is right here. But then that reference angle right there is just pi over 3. See how I'm like splitting it up into sections, and each angle is pi over 3 anyway. So reference angles for radian measures, like I said, are very nice, okay? If none of that is clicking with you, if you're like, I don't really know how you're drawing these angles though, you can always just, especially early on, convert it back into degrees, right? I mean, I can do 11 pi over 6 is the same as if I multiply by 180 and I divide by pi. Remember, that's the conversion factors. The pi's will cancel. And then I can just, on my calculator, do 11 times 180 and divide that by 6, and I get 330. Or you can do 180 divided by 6 is 30, right? So that leaves you with 30 up here, and 30 times 11 is 330. But then once you know that it's a 330-degree angle, now you're just in degrees, and you can go off to the races. It's a little short of 360, so right there. So that's going to be my reference angle. And if this is 330, then what am I left with is 30, and 30 degrees is, of course, pi over 6. So you can go through the process of sort of convincing yourself that way. But as long as you have your angle simplified, your reference angle from the radian measure is really fast. You just sort of have to trust that it works that way, at least for the ones that we see very commonly. If it's like a pi over 12 or a pi over 24 or something like that, you may have to do a little bit more work than that, but we don't see those very often. Okay, so reference angles for all the common angles in trigonometry are way easier for radians than they are for degrees. Okay, that's all I wanted to say about coterminal angles and reference angles. Hopefully seeing me do a couple of them sort of crystallized it for you a bit. Again, I don't think it's a good idea to memorize the different ways of calculating a reference angle. Just sort of knowing what they are is the best way to go about it. And then coterminal angles, easy enough. Just add or subtract 360 or 2 pi, right? I guess I could have just saved the whole video and told you those two things and it would have been fine. But then you wouldn't know what I was talking about. So there you go. Okay, that is all for this video. I will see you guys next time.